In the last lecture, we were considering unsteady heat transport in a cylindrical coordinate system, okay, using separation of variables procedure. So, the configuration consisted of a cylindrical solid at initial temperature Ti, which was and of radius r, and we considered it of infinite extent in the axial direction, which was immersed in a fluid at a different temperature T0, and we were trying to examine how the temperature evolves with time. The unsteady energy conduction equation is given by this. If you recall, the terms on the right side are the spatial derivatives in a cylindrical coordinate system, which arise because the surfaces are curved surfaces. The surfaces of constant coordinate are curved surfaces with a boundary condition and an initial condition. And when scaled by the distance is scaled by the radius, the scaled temperature is defined in this manner, so that the temperature far from the cylinder is 0, and initially within the cylinder the temperature is 1 at all locations, and the energy balance equation reduces to this form, and we get the boundary and initial conditions. Recall, there was one initial condition at the center which resulted from the symmetry at the center along the axis, because the domain in the radial coordinate varies from 0 to 1. However, at r star is equal to 0, there is no physical boundary, and therefore, we have a symmetry boundary condition at this location. We had separated the temperature into a function of r and a function of t, and used separation of variables, substituted in the equation, divided by f times g, and both the right and left sides are constants. The constant has to be negative because the function is decreasing, the transient part of the temperature is decreasing with time. Note that the steady part of the temperature in scaled form is identically 0 throughout, because the temperature is a constant in the long time limit. And the solution of the spatial problem for the function f, we had got it as Bessel functions j0 and y0, and j0 has 0 slope at the center, and then it has an oscillatory behavior, and it crosses 0 at an infinite number of discrete points. And from the boundary condition that the temperature has to be 0 at the surface at r star is equal to 1, we were able to identify discrete values of this coefficient beta, okay, the constant beta that emerged from the separation of variables. And then we got the temperature in the form of a series, and the coefficients. So, this solution for the temperature satisfies the boundary conditions, because J0 satisfies the boundary conditions, and it satisfies the equation because we got it by separation of variables. What it does not yet satisfy is the initial condition, and that initial condition is determined from the orthogonality relation, because it turns out that these functions J0 of beta I r and beta j r, where beta I and beta j are the values at which the function passes through 0, where beta I and beta j are the values at which this function J0 passes through 0, discrete values. If you multiply J0 of beta I r and J0 of beta j r, it is 0 if I is not equal to j. In other words, if you multiply two different functions, it is 0. If you multiply the function with itself, of course, it has to be positive, because the integrand is a positive number. The square of a number is a positive number. Okay. So, because the integrand is positive, the integral has to be positive. Okay. And we got the solution, and we looked at some of the properties. Okay. At late times, when t star, the scaled time, scaled by the diffusion time for a length r, when that is greater than about 0.1, even including just one term in the expansion gives you a numerically accurate result. At 0.03 you need to include 3 terms, and at 0.01 even 5 terms does not give you an accurate result, though it is close. Okay. And at very early times I had told you that you can use the similarity solution when the penetration depth is much smaller than the cylinder radius. That is, when the depth to which the disturbance to the temperature has penetrated is much smaller than the radius of curvature of that surface, it effectively resembles conduction into an infinite medium, okay, and that solution can be used in this case. And I had derived for you why the orthogonality relation works for Bessel function when the boundary conditions are homogeneous. Okay. When the boundary conditions are homogeneous, okay, you can show that the two different functions when multiplied by each other and integrated, in this particular case the integral is defined with respect to r dr. Okay. When two different functions are multiplied and integrated, integral defined with respect to r dr, the integral is 0 if I is not equal to j. Okay. If I is equal to j, of course, one has to evaluate what that integral is. Okay. So, this orthogonality relation can always be used in order to determine the solution by separation of variables. Okay. We will consider another example of separation of variables, that is the startup flow in a cylinder. Okay. So, I have a cylinder . Of radius r. Okay. This is the axial direction. Okay, I will call that the x direction, and r is the radial direction. And if I look from above, this is the cylinder, okay, and this is the radius r, and this is the radius of the cylinder. Okay. Initially, the cylinder is stationary, okay, and the fluid inside the cylinder is also stationary. At time t is equal to 0, I start rotating the cylinder with an angular velocity omega. Okay. Of course, in the long time limit, the cylinder and fluid will be executing solid body rotation. Okay. So, if I take the velocity in the tangential direction as v phi, okay. If I take the velocity in the tangential direction as v phi, what we have is that at t is equal to 0, v phi is equal to 0 for r less than r. Okay. That is, at time t is equal to 0, the fluid is stationary, you have just started the cylinder moving. Therefore, the fluid is stationary for r less than r, and the boundary condition is that v phi is equal to r omega at r is equal to r. Okay. So, at the surface of the cylinder, the velocity of the cylinder and the velocity of the fluid have to be equal. Therefore, v phi has to be r times omega. Okay. What would you expect in the long time limit? Okay. The steady solution okay, the steady solution v phi s, in the long time limit you would expect both the cylinder and the fluid to be rotating as a solid body, and therefore, the velocity has to be equal to the radial as at a given location times omega. Right. The angular velocity at a distance r from the axis of rotation should be r times omega, okay, for the cylinder rotating. So, that is the steady solution. Okay. And what we need to find out is that how does the velocity profile progress from this initial solution where the fluid is stationary to the final steady solution where it is rotating as a solid body. Okay. So, that is what we have to find out. Okay. So, scaled coordinates r star is equal to r by r, because capital R is the only length scale in the problem. Okay. V phi star is equal to V phi by r omega. Okay. The velocity at the radius r at the cylinder surface, okay, at the surface of the vessel. Okay. And if you use this, then if you use the diffusion time, this T star will basically be equal to T into nu by r square, the time for momentum diffusion over a length scale r. Okay. In case of thermal diffusion, it was alpha. In this case, it is nu, the kinematic viscosity. Okay. So, the boundary condition in that case translates to V phi star is equal to 1 at r star is equal to 1. Okay. That is what it translates to. Okay. And the steady solution is that V phi star is equal to, okay, V phi by capital R into omega. Okay. V phi star is V phi by capital R into omega, which will be basically R by R, which is equal to R star. Okay. That is the steady solution. Okay. That is the steady solution, and the initial condition is that V phi is equal to 0 at R is equal to 0. So, we have to solve the conservation equation subject to these conditions. Okay. Okay. So, the conservation equation we had earlier seen for this tangential velocity is different from that for temperature, concentration and the axial velocity. The conservation equation for this tangential velocity is partial phi v by partial t is equal to nu into partial by partial r of 1 by r d by dr of r v phi. Okay. And I can expand this out, okay, which is equal to nu into d by dr of, okay, this will be 1 by r d v phi by dr plus v phi, okay, and this is equal to nu into, okay, 1 by r I am sorry, this is made a mistake here, okay, dv phi by dr plus v phi by r. Okay. Let me write that again for you. Okay. Differentiate using chain rule, and I will get d phi by d plus v phi by r. Okay. So, this becomes d square v phi by dr square plus 1 by r d v phi by dr minus v phi by r square. Okay. That is the conservation equation in this case. Note that this term, which is present for the phi velocity, was not present earlier for the temperature and the concentration fields. Okay. So, this is the velocity. Okay. So, now using this scaling, okay, okay, it is easy to see that the velocity will be of the form partial v phi by partial t is equal to partial square v phi plus 1 by r partial v phi by partial r minus v phi square. Okay. That is the conservation equation. Okay. Subject to the boundary conditions. Okay. The boundary conditions are, okay, at r star is equal to 1, V phi is equal to 1. Okay. That is this one. Okay. At the surface of the cylinder, the angular velocity is omega times capital R, the angular velocity of the surface. So, V phi star is equal to 1. Okay. The initial condition, okay, at T star is equal to 0, the velocity is 0 everywhere for r less than 1. Okay. Everywhere within the fluid, V phi is equal to 0. Okay. The axis, so the radial coordinate, scaled radial coordinate varies between 0 and 1. Okay. 0 is the axis. At the axis itself, we do not have a physical boundary. Okay. Therefore, the boundary condition at the axis has to emerge from the symmetry condition. In this particular case, the symmetry condition is slightly different. Velocity V phi is the radius times the angular velocity, okay, radius times the local angular velocity. Okay. In the limit as the radius goes to 0, if the angular velocity is finite, then V phi has to go to 0. Okay. The angular the velocity V phi is equal to the tangential velocity, which is the radius times the angular velocity. In the limit as r star goes to 0, if the angular velocity has to be finite, then the V phi has to go to 0. Otherwise, if V phi is finite and the radius is going to 0, it means that the angular velocity is going to infinity, which is unphysical because there is no physical boundary at this location. Okay. Therefore, the symmetry condition in this case is that at r star is equal to 0, V phi is equal to 0. Okay. That is the symmetry condition. Okay. So, those are the initial and the boundary conditions, and we have the steady solution V phi steady is equal to r. Okay. So, now we have to express the velocity as the steady plus the transient part. Okay. V phi is equal to V phi steady plus V phi transient, okay, which means that V phi transient is equal to V phi minus V phi steady. Okay. We know that the steady part of the solution is just equal to r. The steady part of the solution is just equal to this. Therefore, the transient part is equal to V phi minus r. Okay. Now, we have to write the boundary and initial conditions for the transient part. Okay. As we did earlier, we have to write the boundary and initial conditions for the transient part. Okay. For the transient part, okay, at r star is equal to 1, V phi is equal to 1, and the steady solution is also equal to 1. Okay. Okay. And that implies that V phi transient is equal to 0. Okay. Because V phi transient is the total solution minus the steady solution. Okay. And at r star is equal to 0, V phi is equal to 0, and the steady solution, okay, the steady solution, which is this is also equal to 0, okay, which implies that the transient part is also equal to 0. Okay. Those are the boundary conditions, and the initial condition is that at T star is equal to 0, V phi is equal to 0 for r less than 1. Okay. Everywhere within the cylinder, the velocity is equal to 0. The steady solution is equal to r star. It is independent of time. Okay. The steady solution is equal to r, it is independent of time, okay, which means that the transient part is equal to minus r. Okay. That is the initial condition. Okay. So, by subtracting out the steady solution from the total solution, we have obtained an equation for the transient part. Okay. The equation for the transient part is the same as the original equation. Okay. The original equation minus the steady part. The steady part satisfies the steady equation. Therefore, the equation for the transient part is the same as the equation for the original solution, that is partial V phi by partial t is equal to, okay, this is all for the transient part, okay. The equation for the transient part is the same as the equation for the total velocity, because the steady velocity satisfies the same equation. So, when you subtract out the steady part from the total solution, you get the equation for the transient part. And for the steady part, this equation right and left sides are both equal to 0, as you can easily verify. Okay. Okay. So, we have to solve this equation, and we solve it using separation of variables, okay, subject to these initial and boundary conditions. Okay. Express V phi t is equal to f of r g of t. Okay. Substitute into the equation and divide throughout by f times g, and I will get 1 by g dg by dt should be t star. So, okay. Now, right and left sides are both left side depends only upon t, right side depends only upon r, and therefore, both of these have to be equal to constants. That constant has to be negative, so that g decreases exponentially with time. Okay. So, that g decreases exponentially with time. Okay. Okay. The left side has to be negative because g decreases exponentially with time, so that the transient part goes to 0 in the long time limit, and the solution becomes the steady solution. Therefore, g has to be negative. Okay. And the solution for this is, of course, g is equal to e power minus beta square t. Okay. Now, I have to solve the other part, okay, that is d square f by dr square plus 1 by r df by dr minus f by r square is equal to minus beta square f. Okay. So, this equation I can recast it slightly. Okay. Take the right side to the left and multiply throughout by r square. Okay. So, I will get r square plus r df by dr minus f plus beta square r square f is equal to 0. Okay. So, just recasting this equation. Now, you can see that the first three terms on the left have equal dimension in r. Okay. You have r square d square by dr square, r d by dr, and f which does not contain factors of r. Okay. Therefore, if I define R plus is equal to beta R star. If I define R plus is equal to beta R star, then the equation reduces to R plus square d square f by d R plus square plus R plus df by dr plus minus f plus R plus square f is equal to 0. Okay, that is the equation that we get. Recall that when we calculated the development of the temperature profile in the cylinder, when we calculated the development of the temperature profile, unsteady development of temperature profile in a cylinder, I had written for you the Bessel function. The equation, the Bessel equations was x square d square f by dx square plus x df by dx plus x square minus n square f is equal to 0. That was the Bessel equation. And you can see that this is the same as the Bessel equation with n is equal to 1. This is the same form as the Bessel equation with n is equal to 1. So, therefore, the solutions of these are Bessel functions with n is equal to 1. When we did the problem of heat transport in a cylinder, in that case the solution was the same as the Bessel equation with n is equal to 0. And that is because the form of the differential operator was different. If you recall that the differential operator, if you recall here, this was the Bessel equation that I had, and I told you that this the equation that we get over here corresponds to the Bessel equation with n is equal to 0. That was because we had a slightly different form for the operator here. The operator was 1 by r d by dr of r times df by dr. In this case the operator is different. In this case the operator is different. The operator in this case is d by dr times 1 by r d by dr of r v phi. And because of that the solution is slightly different. So, we will continue this in the next lecture. We will examine the properties of this Bessel function solution for this particular case, and also examine the numerical convergence of the solution. I will continue this in the next lecture. I will see you then.